Number 9, the only inside function is the sine of theta. So u is equal to the sine of theta. Second step, u becomes du. We take the derivative, which is the cosine of theta, and we toss d theta on the end. Third step, let's go and diagram. This piece here, now remember, sine to the 5th of theta is the same as the sine of theta all to the 5th. So that piece is going to be replaced with u to the 5th. So what is left? The cosine of theta d theta is left. That's what needs to be by itself right here. It already is. So this is an example of, hey, no adjustment is needed. The fourth step, we rewrite the integral. Again, this piece becomes u to the 5th. And to replace the cosine of theta d theta, that is equal to du. That gets replaced with du. So this replaces sine of theta to the 5th. This replaces cosine of theta d theta. The fifth step, we finally take the antiderivative. The notation drops out. There's nothing to come along for the ride, so we use the power rule to take the antiderivative of u to the 5th. And that is u to the 6th over 6. And then we rewrite it as 1/6 u to the 6th plus c, and plug in u, sine of theta. And there's your antiderivative. Number 10, there is no inside function. This is just 3 polynomial terms. So this is just going to be power rules. All right, so it's always good to recognize when to use u substitution and when to use the power rule. So the antiderivative of x squared is x to the 3rd over 3. Second term, the 4 comes along for the ride, and that becomes x squared over 2. And 1, remember, 1 is the same, any number is the same as x to the 0 afterwards. So when we use the power rule, we get x to the 1st over 1 plus c. And then we rewrite it. 1/3 x to the 3rd minus 2x squared plus x plus c. Number 11, the inside function is x to the 3rd minus 6. The differential, u becomes du. We take the derivative, which is 3x squared. We put dx on the end. Now when we rewrite this, this piece here is going to become u to the 2nd. So I need to replace dx. I need to get dx by itself right here. So that means I'm going to have to divide by 3x squared. So I'm going to get 1 over 3x squared du is equal to dx. Now when I rewrite the integral, the elongated s comes along for the ride. This, of course, becomes u to the 2nd. And I replace this dx. Dx is now equal to 1 over 3x squared du. But there's a big problem here, because the notation will drop out, but this will not come along for the ride. That is not a coefficient because there's an x there. So this is an example of a function that u substitution does not work on. U substitution isn't the end-all be-all. There are some functions where it simply doesn't work, and this is your hint. If you ever come along something like this, u substitution will not work. We don't know how to take the antiderivative of a fraction, and we have two things multiplied together here. So u substitution does not work. So what else can we do? Well, the only other thing we can do is use the power rule. So luckily, this is a squared. So I can simply square that out and then use the power rule. So let's do that. X to the 3rd minus 6 squared is the same as x to the 3rd minus 6 multiplied by itself. Now I can multiply that out either by FOIL or area boxes and use the power rule. When I FOIL that out, I get x to the 6th minus 12x to the 3rd plus 36. Now I can just use the power rule on each term. So I get x to the 7th over 7 minus 12x to the 4th over 4 plus 36x to the 1st over 1. And then I just rewrite it. 1/7 x to the 7th minus 3x to the 4th plus 36x plus c. So if u substitution doesn't work, you just have to go back to algebra and get it to the point where you can use the power rule. Number 12, there are two inside functions here. Remember, secant squared of x is the same as the secant of x all squared. So there are two inside functions. You have tangent of x and secant of x. So when that happens, only one of them is going to work. And here's how you pick. You look for the one whose derivative is right there. All right? The derivative of the tangent is secant of x, or is secant squared of x. So that's why we pick the tangent. So we're going to make u the tangent of x. U becomes du. We take the derivative. Again, the derivative of the tangent is secant squared of x, and we put dx on the end. Now, this piece here is going to become e to the u. So this is what's left. That's what has to be all by itself here. And it already is. So this is an example of there is no adjustment needed. Fourth step, we rewrite the integral. This piece, e to the tangent of x, gets replaced with e to the u. And I replace secant squared of x. Secant squared of x is now equal to du. So a nice, easy integral. The only thing that we need to take the antiderivative of is e to the u. And the antiderivative of e to the u is e to the u plus c. And finally, plug in e to the tangent of x plus c. Number 13, hopefully you recognize this from your derivative flashcards. There is a trig function whose derivative is cosecant squared of x. If you remember, the derivative of the cotangent is negative cosecant squared of x. So the antiderivative of cosecant squared of x would be negative cotangent of x plus c. All right, to check that, we would take the derivative. Hey, that -1 would come along for the ride, and the derivative of the cotangent is negative cosecant squared of x. So that negative and a negative would give us a positive. So this is one where, of course, we don't need u substitution. Hopefully you just recognize this from your derivative flashcards. Part B, this is an exponential function, base 8.4. So we can just use the formula for the antiderivative of an exponential function. So we take and we rewrite the function as is, 8.4 to the r. We divide it by the natural log of the base, 8.4. And we just follow that formula. Exponential function of any base, the antiderivative of, other than e, of course. Number 8, I rewrote it and got rid of that weird trig notation. So this is the same as this, and you can easily see there are two inside functions. Which one should you pick? Well, which one is the derivative of the other? The derivative of cotangent is negative cosecant squared of x. So you will be able to adjust that. So again, pick the function whose derivative is sitting right next to it. So u is going to be the cotangent of x. The differential u becomes du. We take the derivative, which is negative cosecant squared of x, and we put dx on the end. The third step, let's go and diagram. This piece here is going to get replaced with u to the 8th. What's left? Cosecant squared of x dx is left. That's what has to be by itself right here, but we have a negative cosecant squared of x dx. So our easy adjustment is just to divide through by -1. So we have negative du is equal to positive cosecant squared of x dx. All right, now let's rewrite our integral. So the fourth step, I'm going to squeeze it in. This piece becomes u to the 8th. And I replace cosine squared of x dx. Our differentials tells us that that whole thing is equal to negative du. Fifth step, I take the antiderivative. Don't forget that -1 comes along for the ride. The notation always drops out. You will have one thing left. We have u to the 8th, and that's what we take the antiderivative of, and that's a power rule. So we get negative u to the 9th over 9 plus c. And now we rewrite it. Pull out the -1/9 and write it as a coefficient. Plug in u, cotangent of x, plus c. And there's your antiderivative. Okay, number 15. This is a tricky one, and there is a little trick that you can do to get this to work. But let's get into it and see why u substitution doesn't work when the function is written like this. I rewrote it, and I got rid of that weird trig notation, and that allows us to easily see that our inside function is the secant of x. So u is equal to the secant of x. U becomes du. The derivative of the secant of x is secant x tangent x. I toss dx on the end. Now, let's go up and diagram. This piece here is going to become u to the 7th. But that means that I have to replace the tangent of x dx. So in order to get the tangent of x dx all by itself right here, I would have to divide by the secant of x. So if I were to divide by the secant of x, I would have 1 over the secant of x du is equal to tangent of x dx. Now, when I rewrite the integral, this piece would become u to the 7th, and that's fine, but I would have to replace this. The tangent of x dx would be replaced with 1 over the secant of x du. Now, the problem is this is not a coefficient. This will not come along for the ride, so it doesn't work. But here's what you can do. Check this out. I can rewrite this again. I can pull out one of these secants. So it's going to look like this. What if I rewrite this again? And I have 6 secants here, but I put one here. Okay? These are equivalent. The secant to the 6 times the secant gives me 7 secants, and that would make this work. So let's do it this way. Let me get rid of all of this, and let's make it work. Now watch what happens. Now, this piece here is going to get replaced with u to the 6. Now I need to get the secant of x tangent of x all by itself. And it already is. So that's an easy trick you can use to get u substitution to work. That means there is no adjustment needed. All right, when I rewrite my integral, again, this piece becomes u to the 6th. And I replace secant of x tangent of x dx, that whole thing is equal to du. All right, now I finally take my antiderivative. The notation drops out. I have to use the power rule here, and that becomes u to the 7th over 7. And then finally, I pull out my coefficient, 1/7, and I plug in u, 1/7 secant of x to the 7th plus c. All right, please go through this one on your own. This is a tricky one. But if you get to the point where u substitution doesn't work, another option is see if you can rewrite the function a little bit so that you can get it to work. Thanks, calculus.